Polynomial inequalities can be solved by finding the zeros, then either graphing or testing intervals between the zeros. So our first example, we're going to clarify what it means to state the intervals when the function is above 0. So that is this one right up here. So we're looking for f at x is greater than 0. So the first thing that we're going to do is identify the locations where our function crosses the x-axis. So it crosses at -5, -2, 1, and 3. I'm going to use my red here to highlight all the areas that are above the x-axis, which is where the y value of the function is greater than 0. So that is these three sections right here. So when I go to state my interval, I'm always going to talk about it in terms of x. And I'm going to say that x goes between -5 and -2. It also goes between 1 and 3. And then it also goes between 3 and positive infinity. Those are the x values of the three sections I've highlighted in red. I'm using open brackets, not closed brackets, to show that the zeros are not included because the function is equal to 0 at that point, not greater than 0, which is what the inequality symbol implies. The second one down here, we're going to take a look at when it's less than or equal to. So that means I'm going to highlight the sections that are less than. So that's these two that are in blue. And I'm also going to highlight the zeros because my function says, or my inequality says that it's less than or equal to 0. So then when I go to state my solution, I'm going to say that x goes between -infinity and -5. Also goes between -2 and 1. And then it also includes the number 3 because that is a 0. I also need a closed bracket here on the 5 to show that it is included because it is equal to 0 at that point. So let's take another look at an example down here. These ones have an equation, but no graph. And we want to know when the function is less than or equal to 0. So the first thing that I have to do is to actually sketch the graph. So I notice for my n behaviors, I notice that my degree is odd and my leading coefficient is negative. So that means that my function is going to look like this, going down to the right. My zeros are easy to identify because it's already in factored form. I have a 0 at x equals 3, and I have a 0 at -1 that has multiplicity of 2. So I know it only touches the x-axis at that point. So I'm going to put on my zeros at 1, 2, 3, and then at 1. I know that my n behaviors are finishing up like this, and I know I passed through my first 0. Should probably find my y-intercept too. So my y-intercept, when x is equal to 0, I would get 1 times 3. So x is equal to 0, so I have 0 minus 3 is going to be 3 here. So I know that my n behaviors are actually not going up and to the right, they're going down to the right, which makes more sense here. My y-intercept is right here, so I know that my function is going to come down and touch 1, and then it's going to turn up and turn back down, which fits my n behaviors as well as my zeros. Now I'm looking for the sections of the graph where my function is less than or equal to 0, so I'm going to use blue again. I'm going to highlight the sections of the graph where the function is less than 0, which is right here, and equal to, which is the zeros on my graph. And then I'm going to describe the solution in terms of x. So x is equal to 1, and it's also equal to all of the values that are 3 and more. All of those values satisfy the function being less than or equal to 0. Let's graph the second one. So for my n behaviors, I see that my leading coefficient is positive, and I can see that my degree is 1 plus 3 is 4, 4 plus 2 is 6, so that is even. So then I know that my n behaviors are going to look like this. My zeros are x equals 0, x equals 2 with a multiplicity of 3, x equals minus 1 with a multiplicity of 2. And then I'm going to find my y-intercept just to help me sketch the graph. When x is equal to 0, y is equal to 0 because of this extra factor right out here. So there's my x and y-intercept. Got an x-intercept at 2, x-intercept at 1. When I come down at 2, I have a multiplicity of 3, so I sort of go through that. Try that again there. So I go through it kind of like a cubic. I'm going to come up to 0 and pass through, down to minus 1, touch but not cross, and then go back up. And here I'm looking for the spots where my function is just greater than 0. So that would be on the right-hand side here, in between these two zeros, and on the left side right here. So when I go to describe that, I'm going to use my x values. I'm going to say that it goes from minus infinity up to the first 0, which is minus 1. Then it goes in between the next two zeros, minus 1 and 0. And then it goes on the other side of the final 0, which is 2. You can also use a chart to test the intervals. So this is the same function that we did up here that we sketched. And I know that my solution to the equation was this, x equals 1 and 3 to infinity. So we're going to use the same idea to check these values here. So I'm going to make a number line, and I'm going to put my zeros on it. So I've got a 0 at 3, and I've also got a 0 at 1. Now, a function can only change signs at the x-intercepts. So what I need to do is test values that are in between those values and compare them and see if they're positive or negative. So I'm going to check on the left side of 1, I'm going to check 0. I'll write these in red. So x equals 0 is my test value. In the middle, I'm going to check 2. And then on the right-hand side, I'm going to check 4. So now I'm going to put all my factors down the left-hand side. So I've got minus 1 from the minus in front. I've got x minus 3, and then I've got x minus 1 squared. So when I put in 0, I know that when I put in 0 and I have a negative 1, I still have a negative sign. When I put 0 into this bracket, 0 minus 3 is minus 3, which is negative. And then what I notice is that I'm substituting in a value and then I'm squaring it. So it's always going to be positive, which means that in this interval between minus infinity and 1, my function is going to be positive. In the middle, I'm substituting in 2. So my first one is always negative because it's just negative 1. 2 minus 3 is also negative. This last one is going to be positive. That means that in this interval, my function is also positive as well. In the last one, I'm substituting in 4. I have a negative for my negative 1, a positive for 4 minus 3, and then a positive here. So that means that my function is negative on this interval. So then when I go to state my solution, I'm going to say that x is equal to 1 or equal to 0 at my first x-intercept, which is here, but it's not equal to 0 in either of these intervals. It's only equal to 0 on the right-hand side, which is the same answer that I got when I used the graph. So let's take a look at one more example. You might notice that this one is not factored. So the first thing that you do need to do is to factor this one. So let's check a possible value. We're going to check f at 1, which is not 0. And then we're also going to check f at minus 1, which is 0, which means that x plus 1 is a factor. And so I'm going to divide that out. I've got a minus 1 over here. I'm going to put my coefficients across, 12 and 16. And I'm going to perform synthetic division to get that across. Minus 16, I know it's a factor. That means that I can rewrite my function as, let's do a couple things here. I'll do that after. Okay, I can rewrite this as x plus 1 times minus 2 x squared minus 4x plus 16. Now what I'm going to notice is that everything in that quadratic is divisible by minus 2. So I'm going to pull that out in front. And that's going to leave me with x squared plus 2x minus 8. This leaves me with a quadratic that I can factor. I've got minus 2, x plus 8, x plus 4, and then x minus 2. So for this last one, we have our factored form of the equation, which is minus 2 times x plus 1, x plus 4, x minus 2. And we're going to set up our number line with our zeros. We've got x equals minus 4, x equals minus 1, and x equals 2. And then we're going to check our test values in between those x intercepts. So I've got minus 4, minus 2, 0, and 3. And then I'm going to write my factors down on the left-hand side. So I've got minus 2, x plus 1, x plus 4, and x minus 2. And then I'm going to substitute in my test value to check the sign. So the first one is minus. Minus 5 plus 1 is going to be a negative number. Minus 5 plus 4 is also a negative number. And then minus 5 minus 2 is also a negative number. So overall, the function is going to be positive in that interval. If I move on to minus 2, the first one is negative. Then I've got minus 2 plus 1 is negative. Minus 2 plus 4 is positive. And minus 2 is negative, which means that in the second interval, my function is going to be negative. In my third interval, now I'm substituting in 0. I still get a negative here. Positive, positive, negative. So overall, my function is positive. In the last interval, when I'm substituting in x equals 3, I'm going to get a negative, a positive, and a positive, which means overall my function is negative in that last interval. So the question is asking me to look for, doesn't say, but we did less than or equal to. So let's do f at x greater than 0. So that means I'm looking for my positive intervals, which is this first one and third one. So then I would say that my solution would be that x is in between minus infinity and minus 4, exclusive, because I'm looking for just greater than 0. And then I'm also looking for between 1 and 2, exclusive because my x-intercepts aren't included.